So, good afternoon, everyone, and welcome to Code That Fits Your Brain. What I want to do in this session is that I would like to look at how we can make code fit the way we think, remember, and reason. And the promise would be that such code would be easier to understand and easier to maintain, which in turn would translate into direct savings. And I mean savings of both time and money, and most important, frustration. So we're going to look at code through the lens of psychology. So let me tell you a little bit about my psychology background. I've been a software developer for 23 years now. And if those 2 decades in the software industry taught me anything, it is that code is ridiculously hard to get right. And it's ridiculously hard to maintain it. And in turn, it's really, really hard to succeed with large-scale software development. And after spending the first 10 years in the software industry, I kind of wanted to figure out why is that case? Why is it so hard to succeed with delivering successful software? And I decided to look outside our technical field. I decided to pick up psychology because I thought that psychology is about people like us, people who actually write code, right? So by learning how people reason, how we think, how we remember, maybe we can draw some lessons back to programming that can benefit our code. And I ended up spending 6 years at the university, ended up with a master's degree in psychology. And at the same time, I was fortunate to work as a software consultant. So I got plenty of opportunities to kind of relate these two fields. And I've written 2 books about it so far, about this intersection of psychology and technology. Your Code is Crime Scene, and my most recent book, Software Design X-Rays. And when I set out with my psychology studies, I basically wanted to answer the question, why? Why is it so hard to write good code? After 6 years in psychology, I came to the conclusion that it might be a good question, but it's also the wrong question to ask. Because what I learned within psychology was that I got surprised that we're capable of writing any code at all. It just shouldn't be possible. Writing software should be too hard for us. The human brain is way too limited. So what I think now is that instead of asking why it's so hard to write good code, a much better question is to not asking why programming is hard, but rather why it's possible at all. Because after all, we write code almost every single day, and occasionally our code even works. And the reason for that is because even though the human brain has a bunch of different cognitive bottlenecks, we, as humans, we have also evolved some pretty good workarounds around those bottlenecks. And that's what I want to look at today. We want to design software as if people matters. And one of the guiding principles that you will see throughout this presentation is this: beauty. And the reason I want to start by talking about beauty is because beauty is something that has a profound impact on all of us. It's also a very well-studied research topic. So, for example, did you know that beautiful people, you know, when we see a beautiful person, not only are we considering them as being more friendly and open, but we also consider them to be more intelligent and competent based on appearance alone. This isn't fair, is it? No, it definitely isn't. But on the other hand, it's great news for us here in this session, right? So beauty has a profound impact on us, how we perceive other people. But what is it actually, and why does it relate to code? Well, let's look at my favorite definition of beauty. If you look at these 2 persons, they actually won a beauty contest. And that's nothing special in itself, is it? Because, I mean, they are both pretty good looking. What I find extraordinary is that none of these 2 people actually exist. These photos were created as part of our psychology research project. And what the psychologists did here was pretty fascinating. They took photos of individuals and then they used computer software to morph them together to combine multiple photos into a single image. And what they found out was that the more photos they morphed together, the better looking the end result was. And this is interesting because if we consider what actually happens when you start to morph photos together, it is that individual differences disappear. And the end result goes more towards an average. And that means that my favorite definition of beauty is this. Beauty is simply average. But it's not average in the sense that it's ordinary or common. No, it's ordinary. It's average in a mathematical sense. A mathematical average is indeed a rare thing. What I also find so fascinating about this research is that beauty turns out to be defined not so much about what's present, not so much about what's there, but rather about the absence of something. You can basically say that beauty is the absence of ugliness. It's an average. So beauty is a negative concept, but why does it have such a profound impact on us? The leading theory in psychology is something called the good genes theory. And if we think about this, we take a step back and we look at life in a much, much larger evolutionary perspective. In that perspective, as humans, our main task is basically to reproduce, to create more humans, the next generation. And if you think back to where we came from, let's think back to Stone Age. If you wanted to reproduce, you need to find a partner. And to find a partner, you obviously wanted a partner with good DNA, with good genes. However, back in the Stone Age, it was pretty hard to come by DNA tests, right? Not many of them around at that time. And today, when we have them, it might simply not be socially or culturally acceptable to ask for that, right? So the theory here is that humans have evolved to use beauty as a proxy for good genes. And the idea is, if you think back to the definition, that if you could grow up having a symmetric and mathematical average face, then that could indicate that you have a good immune system that kind of prevented you from infectious diseases. So beauty is a proxy for good genes. And when I read about this theory, I started to think, could there be something like a good genes theory for code? What would healthy code look like? What would code with a healthy immune system look like? And I want to look at two different examples here today. And the first one I want to look at is what we call working memory, which is a psychological construct that I'm going to talk about soon. But before I do that, let's look at some code. So as part of my day job, what I do is I develop a tool called CodeSim. And CodeSim's main task, one of its main areas, is to prioritize technical debt. And as such, I analyze lots of different code bases. And you see an example here in the visualization. It's what I call a hotspot visualization, where the large red circles represent potentially problematic areas of the code base. And when I find a hotspot, I pick up the code and I look at it. And a pattern I almost always find is what you see to the right. This specific example, this code sample, is from the React project from Facebook. And the pattern I'm referring to here is this: deeply nested logic. It's so common. And deeply nested logic in this shape is also better known as the dreaded arrow pattern, right? By the way, this is one of my favorite images ever. And I would like to show you why deeply nested logic, that is having if statements inside other if statements, why that kind of code is a problem, always. And the way I want to show you that is by having you do an IQ test. Yeah, that's not fair. You weren't prepared for that at all, were you? No. But you see, that's what happened when you let a psychologist into a session. All right, let's take this easy. Let's do it together. I just want to show you a couple of examples. So if you ever tried an IQ test, a very common method is that you're shown a matrix with a bunch of different patterns, and one of them is missing. And your task is, from the two bottom rows, pick the missing piece. And if we look at this matrix, we see that, all right, we can view it as either columns or we can view it as rows. No matter what, if we take the first two images and we combine them, then we end up with the image in the third row. And using that rule, we can quickly identify that image number 8 is the missing piece here. That was pretty straightforward, wasn't it? Let's raise the bar a little bit. Let's look at a slightly harder test. All right, so what piece is missing here? Well, I personally found this one much, much harder, because what we need to do now is that we still need to remember those two different images if we view it as rows or columns. And we need to combine them, but we also need to subtract the elements that overlap. And if we do that, we end up with this answer. My guess is that you also thought that this second test was a little bit harder. And the reason it was harder was because in the first case, you just had to keep two things in your head, right? Two different patterns that you combine. Here, you had to keep much more information in your head. Not only did you have to remember the different patterns, you also have to merge them together. You have to identify the overlaps, and you have to reason about the resulting image. And the reason this one was much harder is due to something called working memory. So working memory is like the mental workbench of your brain. It's working memory that you use to perceive, interpret, and manipulate information in your head. So working memory is vital to a lot of different tasks. It's working memory that you use when you solve a Sudoku, you play chess, or you reason about code. So working memory is vital to us as software developers. The problem with working memory is that it's also a strictly limited cognitive resource. There's only so much information we can keep in our head at once. And if you look at modern psychological research, it turns out that it might be as few as 3 to 4 items that we can keep in our head at once and reason about them. So let's take what we saw in the IQ test. The more items we have to keep in our head, the higher the load on our working memory, and translate that into programming. What would those different things be that we need to keep in our head and reason about code? In programming, those things translate into state. So let's return to our React example. Let's pick it up again. So here's the React example I showed you a couple of minutes ago with the deeply nested logic. And let's say that we are going to do a bug fix here. We're going to modify a particular line of code. And what's interesting here is that if we make that modification, we now have to do that modification while maintaining not only 1, 2, 3, 4 different things in our head. So we need to keep 4 different states in our head when doing this particular change. And that basically means that when working with code like this, we're operating at the edge of our cognitive capabilities. And there's no wonder that things go wrong, because the human brain simply cannot keep all that information in our head and reason about it effectively. And this is supported by some very good research on large telecom systems, where it turns out that constructs like deeply nested logic are responsible for roughly 20% of all programming mistakes. So my first recommendation is don't turn your code into an IQ test. But let's say we ended up there. Our code is indeed an IQ test. It's really tricky. How can we refactor a construct like deeply nested logic? Well, we can take some inspiration from chess masters. So what you see here on screen is one of my favorite biographies. This is a book by Frank Brady over Bobby Fischer. So Bobby Fischer is possibly the best chess player who has ever lived. He was an amazing chess player. And Frank Brady in this book knew him very well, and Frank Brady was a skilled chess master himself. And he tells this wonderful story where he played a tournament in New York many, many years ago. Bobby Fischer attended the same tournament, and Bobby had already won his game, so he was on his way out. He left the hall, and he walked by Frank Brady's table, where Frank was in the middle of a chess game, and Bobby Fischer basically just threw a quick glance at the table like this, and then he walked on. Months later, they met again, and the first thing that Bobby Fischer asked Frank Brady was, "Hey, did you play queen to e4? Not only had Bobby Fischer remembered the precise position of each piece, his chess piece, he also had figured out the winning move in his head. And this is pretty impressive. And for that reason, psychologists love chess players, because they give us an excellent opportunity to study working memory and human memory. So if you do a test where you have people trying to remember as many chess positions as possible, it turns out that chess experts, they simply outperform novices like me, right? There's no way I can keep up with that. But then you do an interesting variation on the same experiment. You put up a board with chess pieces, and you organize the pieces in a random order. an order that can never, ever occur naturally during a game. So maybe you put the bishops on the same color. And once you do that, once you randomize a chess setup, it turns out that the experts lose their advantage. They can no longer retain more information than we can. And this is interesting because it kind of indicates that chess players don't necessarily have a better memory. Their memory just works differently. And it turns out that differently is that chess players use a technique called chunking. So chunks means that a chess player, they never remember each individual piece. What they remember instead is groups. They remember patterns. And chunking is the technique of taking some low-level information and putting some kind of abstraction on top of it. And chunking is important because it's a technique that allows us to stretch the capacity of a working memory. We can still only keep 3 to 4 things in our head, but by using higher level abstractions, each thing now carries more information. And chunking is a technique I use all the time when refactoring code. So let's get back for a last time to our React example, the one with the deeply nested logic. So when I come across code like this, the first thing I try to do is to identify the different responsibilities. And then once I've identified those responsibilities, what I do is that I extract each one of them and put the name on that responsibility. And in programming, chunking is represented by the humble function. So I simply extract a function for each of the responsibilities, and with a proper name, that name is going to serve as a high-level chunk that let me reason effectively about the code. And using that technique, I can go from what I see here on the left to the code on the right. And everything I've done now is I applied an automated refactoring extract method, right? 3 times, that's all I did. And the reason I start with chunking is because chunking tends to reveal the overall algorithm, the overall flow of that function. And that tends to suggest the next refactoring steps. So by introducing chunks, I quickly saw that, all right, this looks a little bit like it could be the starting point of refactoring towards the design pattern command, which in turn would make the whole function just disappear and be better aligned with the way our brain prefers to view code. So that was a little bit about memory. I want to talk about one of our other tools as humans, language. And I want to talk about both spoken languages, our natural languages, as well as our programming languages, because they are quite different. But let's start with a small thought experiment. Please have a look at this beautiful, deep red rose. I really love that color. Isn't it beautiful? But now, what if our language, what if English didn't have a word for the color red? Would we still perceive that rose as beautiful? Would it look different to us? There are a bunch of linguists and psychologists that claim that yes, that rose would look different. And that's known within psychology as the Sapir-Whorf hypothesis, that the language that we speak influences the way we perceive the world. And this is something that has been studied with a fascinating group of people in Australia called GOTO. GOTO, the language, has this very fascinating property that they use absolute directions when they reference something. So if you have a conversation with the native GOTO speaker, they might say things like, hey, watch out, you have an ant on your southwest leg. Or you have a mosquito on your north shoulder. Wow, that's kind of fascinating. And since their language has this property, they naturally pay attention to the different geographical directions, meaning they have something like an internal compass, right? They never get lost like I do. On the other hand, studies show that GOTO speakers might have a harder time solving tasks that require relative positioning. So for example, let's say setting a round table with forks to the right and knives to the left might actually be slightly harder for them. And this is an example on the Sapir-Whorf hypothesis at work in the real world. Then, of course, there were stronger statements made. One of them is by this guy, Ludwig Wittgenstein, who claimed that the limits of my language means the limits of my word. And modern scientific research has kind of come to a conclusion that this statement, it's way too hard, it's way too harsh, it's simply not correct. The language we speak doesn't really limit our word, but it influences it. However, I like to claim that within programming, the language influence is much, much stronger. And I think that it can indeed limit our word, or the language we code in can actually expand our word. So I want to give you an example. I want to give you an example from one of my favorite technologies, APL. So if you haven't seen APL before, it really looks like this, like a cursing cartoon character, right? And what this code does here, because it's actually valid APL, is that it draws a series of lotto numbers, 6 numbers, the numbers, random numbers from 1 to 40, and it delivers them sorted in ascending order. That's a lot of behavior squeezed into a single line of code, isn't it? A couple of years ago, I did an earlier session where I presented this APL example, and a very common reflection was that, oh, APL, it's tricky just because it has this odd syntax. It uses some special characters and special symbols. So that may very well be the case. So for those of you who think the same, you have to be relieved to learn that there's another language, an evolution of APL called the J programming language, that restricts itself to pure ASCII syntax. So I took the liberty and took this APL code, the one we saw on the previous screen for drawing lotto numbers, and translated it into J code. Here's what it looks like. Really so much simpler, isn't it? Well, I do think that this example demonstrates that the difference goes deeper than syntax, right? It's not only about the symbols. So it's not a matter of syntax. Array languages, a language family that APL and J are members of, they present a radically different way to code and solve problems. And I like to explore how, because I think there's an important lesson that we can draw from these lesser-known languages. And I like to show that example by introducing one of the worst things that ever came out of programming. I'm talking about this. I'm talking about null references and null pointers. I'm not a big fan of null. The reason I'm not a big fan of null is because if we consider this simple example, let's say we have a string, and we can point our string to some kind of value, right? Let's say put retro games into our string. We can also point it to an empty string. But then we can also assign our string on null. And the moment we assign our string to null, we have basically introduced a special case, because we can no longer use most of the stuff in our string API. What's even worse is that everyone who gets access to that null reference now needs to treat it differently as well. So this is clearly a special case. I would say it's the present of ugliness. So what can we do instead? Well, there have been several attempts at solving null references and null pointers. A very common approach is this: a safe navigation operator, right? Where you can simply chain together deep access like this and have our language prevent null reference errors. And the first time I came across a safe navigation operator, that language support in a language, I immediately thought that this is a very elegant solution to the wrong problem. Because what we do with the safe navigation operator is that we basically put the responsibilities on the consumer and it doesn't really address the root cause. So what can we do instead? This is where I like to draw some experience from array languages like APL and J. Because just to recap very quickly, what these two snippets of code do is that they draw a series of lotto numbers, 6, numbers at random from the range 1 to 40, and returns them sorted. What fascinates me here is that, again, if we take a beauty tool and apply it here, what's fascinating is that you don't have to understand APL or J syntax to see that there is no conditional logic here. There's no if statement here, right? And what's even more interesting is that there are no explicit loops in this code. And that's even though that code models an inherently iterative problem. So to me, this is true beauty. And the reason that array languages like APL and J pull this off is because the array, or collection, is the fundamental data type. So that means that the APL and J, they operate on collections of things rather than individual values. And the implication is that the moment we start to think about data as collections rather than individual elements, we solve a whole set of potential coding issues. So this is one of the most important recommendations I have today. This is something I've been doing myself for years. I have been modeling data as collections and very, very rarely as individual values. And the reason I do this is because the moment we view data as a collection, there's no difference if we have 1,000 of something, a single value, or none. Our code will look exactly the same. And in practice, this is very easy to do. Me, myself, I work mainly in functional programming languages these days. And there it's quite natural because we have tools like map, reduce, filters, and all those goodies. But even in object-oriented languages, we now have built-in support like LINQ for C#, Java has its Streams API, and hey, even C++ got ranges these days. So by following this recommendation, we can get rid of a lot of special cases and make our code more concise and robust. And as a bonus, we also tend to get rid of disastrous null pointers. A small reflection on that. Like I said, this is a principle I've been applying myself for years. And what I also tend to do is that each year I tend to take a week off from work and try to learn something new, usually something tech-related. And last year, I decided to try to implement a neural network from scratch. It wasn't meant to be something you put into production, just be something that I can explore so I can understand what happens under the hood. And I also decided to put some constraints on myself. I decided to try to implement this neural network without using a single explicit conditional. That is, no if statements, no else statements, no switch case, and so on. And the resulting solution was a little bit contrived. I don't recommend that you take this recommendation and apply it as a general rule, because sometimes an if statement is exactly what the doctor ordered. But it's an interesting learning experiment. And what was so interesting with it was, first of all, it was of course doable, but what was interesting was that I found out that once I've written that code, with a single test case at the top, I could achieve 100% code coverage. And this was an interesting side effect. By having everything as a collection and everything as basically a pipeline of operations, there's not a single special case. There's only one main branch through it, right? So things like testing suddenly get pretty interesting. So it was a nice and unexpected bonus. And I'll be happy to talk more about that in the when we get to a question soon. But before I take questions, I would like to leave you with a reflection on the brain. So let's talk a little bit about neurology here. As you might know, the human brain is made up of two different hemispheres. We have the left hemisphere and the right hemisphere. And our cognitive functions tend to be a little bit unevenly distributed. So for example, typically the language center is in the left side of the brain. And the two brain halves, they communicate with each other. They communicate through a thick collection of nerves called the corpus callosum. It kind of connects the two brain halves. Now, what would happen if you would cut the connection between the two brain halves? What if you would cut the corpus callosum? You would basically end up with a person that has two smaller brains inside the same head. And just before I continue, is this some kind of crazy Frankenstein experiment? No, it's not. This is actually a medical procedure used to treat severe cases of epilepsy. So patients who go through this medical procedure, they're referred to as split brain patients. And again, psychologists love split brain patients because they can tell us a lot about how our brain works, how different hemispheres, what the strengths are. So a very typical experiment that you do on split brain persons is that you ask them to please sit down. The person sits down. Then you instruct the right hemisphere, the part of the brain that doesn't have a language center, to please stand up. So the split brain person, what happens in these experiments is that they stand up. And then you ask them, why do you stand up? And now the left hemisphere, the one with the language center, kicks in and answers something like, oh, you know, I got thirsty, so I had to go for a glass of water. They don't answer, which would be much more correct, that, you know what, my two brain halves, they have no connection with each other whatsoever, so I simply don't know. Instead, we make an after-the-fact rationalization. And this is profound, because what it basically means is that our whole sense of free will, our whole sense that we are in control, is an illusion. It's an illusion, and you can basically measure that at a neurological level as well. At the moment we decide that we want to do something, when we become consciously aware of that, the brain has already decided that for us and started to prepare our actions. And this has an interesting implication on us as programmers, because what it means to me is that we really, really have to question who writes our code. So, with that short story, I've come to the end of my session. And if you want to read more about this topic, I have my new book, Software Design X-Rays, where I cover several of these cases and some others and give some examples on different refactoring techniques. I'm also doing a masterclass at Gotopia in just 2 weeks, and I hope to see some of you there. And now, before I take questions, I hope you find this session interesting and that you learned something new. And thanks a lot for choosing to spend 1 hour of your afternoon with me. Thank you very much.